I want to tell you about this strange sounding title, The Value of Errors in Proofs. And the subtitles I'll describe and explain everything. It's a fascinating journey from Turing 1936 paper to the 2020 breakthrough MIP RE. You don't have to know what this is. I'll explain, as I said, everything. The plan is simple. I want to tell you about the errors, the value of errors in proofs. It has impacts on numerous fields, on science and technology, conceptual implications, and in mathematics. But before I tell you about the value of errors in proofs, I'll tell you about value of errors in algorithms, in computation. And even before that, I want to tell you about what proofs and computations are, to put everyone on the same level. Most of all, I guess this chair can move, maybe. It's a story. It's one of the stories that we now have in computational complexity. That's my field. An evolution of one notion through some decades, and by now we have such stories in several areas. I could tell you different ones, but I'll focus on this story of proofs. And it sort of demonstrates this methodology of the field, I think, very nicely. The issue of modeling, of insisting on algorithmic efficiency, on classification of problems into classes, and so on. And we'll see examples of that. So let me start. I guess I started late. I should. I hope I get my 15 minutes or so. Sure. Okay. So proofs and computations go together for many, even millennia. And I'll just tell you about 2 points in this long history. The first one you all know, it's Euclid's Elements, a famous math textbook. And if you read it, you see, axiomatic system, 5 axioms, and then the derivation of many theorems in plane geometry. But if you really read these proofs, you see that they are all algorithms. They are algorithms to construct points in the plane using 2 gates, 2 operations, using a straight edge and a compass. So in plane geometry, really, proofs and computations are the same. Jumping ahead 2 millennia farther to the beginning of the 20th century, Hilbert had a dream that actually what happens in plane geometry happens in all of mathematics. Namely, he believed that mathematical truth is the same as the ability to prove it. And he believed that everything provable can be computable by what he called the mechanical procedure. This dream, wonderful dream, was shattered, as I'm sure you know, first by Gödel, his incompleteness theorem, showing that there are true statements in number theory which are not provable, and then by Turing, which will be our focus here, his undecidability theorem, showing that there are provable statements that cannot be decided. In order to do that, he had to give meaning to what a mechanical procedure is. What did Hilbert mean? He had to define algorithms in the, except that since then, the notion of a Turing machine, what we call today Turing machine. Of course, as a topic I will not go into, this led to the computer revolution we are all part of. I'm talking about theory here, so let's forget about that. What are the algorithms for? In this talk, all algorithms will be for decision problems. What's the decision problem? There is some fixed set S we all know about, let's say the set of primes, and we are given an input, let's say a number X, and we ask whether it's a member of S or not. This is the only type of questions we are interested in, and it captures almost everything we are interested in. And then Turing defined 2 classes, implicitly defined 2 classes, the recursive sets. Those are sets that are computable by finite algorithms, like whether a number is prime or not. And then RE, recursively enumerable sets provable to finite algorithms. So one talks about proofs and one about computations, and he showed that they are different. There are recursively enumerable sets, namely the halting problem, the question of whether a given Turing machine will ever halt or not, and show that it is not decidable, not computable. And then I mentioned P versus NP, we'll see it again and again. I'm sure many of you are familiar with it, but even those who don't, it talks about the same thing, proofs versus computations, not in the setting of finite algorithms, algorithms which hold some time, but rather about efficient algorithms, those that have only polynomial time to work. And other than that, the problems are just the same. Is P equal NP, is proofs and computations the same? We don't know. That's a major open problem that's a guiding light for us. I want to talk about proofs and proof systems, so I'll just run through some examples, but the picture you should have in mind is the following. We just should think when, not necessarily in mathematics, even on discussions with your friends, what is a convincing argument? So we have some claim that a number is prime or that X is in some set S, and there are two parties to this discussion. One is a verifier, who on the one hand really eager to know whether this is true or false, but on the other hand is computationally limited and cannot do it on its own. And so the other party is the prover, who knows everything and can compute everything, but cannot be trusted. So the verifier would like to verify that the claim is indeed true as the prover claims. And so the prover is allowed to send an argument, let's say write a mathematical paper with a proof. Okay, so this is the proof system in pictures. I want to give now concrete examples of some proof systems for particular types of claims. First, proof systems for proving that a number is composite. It's very simple. The claims look like an integer, right? The claim is that it's composite. An argument for it will be two smaller numbers. And what does the verifier do given these two smaller numbers? Multiplies them and see whether it gets the input or not, right? If yes, it accepts, otherwise it rejects. It's a very simple proof system. Of course, I want to stress this again and again. Verifying proofs, verifying arguments should be easy, should be have an efficient algorithm. Here it's just multiplication. This is general, of course. This proof works for any composite number, and the verifier will reject prime that is true. And the theorems of this proof system are simply the set of composite numbers. Those are accepted and the others are rejected. Another thing to stress is that we don't care about the complexity of generating the argument. Maybe very hard to do. Maybe this is factoring integers. We sort of believe, or cryptography rests on the assumption that it's hard to factor. We don't care about it in proof systems. We just care that verification is easy. Okay, let's see another example. Sudoku puzzles, it doesn't have to be serious math. These are interesting too. The claim is that this particular Sudoku puzzle is solvable. How does an argument look? We know how it looks. Suppose you couldn't do it by yourself, but a friend shows you this square filled up with a missing numbers, and then you can easily check, verify that it satisfies all the Sudoku rules, and you accept if it does, and you reject otherwise. Again, very simple to verify. And what's the set of theorems in this proof system? It's all the claims which are accepted, namely all the Sudoku puzzles which are solvable. Of course, those in the newspapers are always solvable, but you can easily make unsolvable ones. And it's general, it's not just a finite set of examples, because you can generalize Sudoku to any dimension. So again, it's an infinite set, solvable Sudoku. Let me jump to something that is very familiar as a proof system in mathematics, piano arithmetic, which is an example of deductive proof systems like Euclid's plane geometry. The objects manipulated here are formulas over integers. This is supposed to capture number theory, for example. We have a bunch of axioms, which are like commutativity and x plus 1 given the bigger than x, induction. And we also have deduction rules to infer some formulas from others. For example, this modus ponens. If we know A and we know that A implies B, then we know that B is true as well. So that's the proof system. How does an argument look for a claim C, for formula C, that the formula C is true? Well, it looks, as we expect, as a sequence of other formulas, and each one of these formulas should either be an axiom or should follow from previous ones using one of the deduction rules. And the last claim is last formula in the chain should be a claim. And again, also here in this much more complicated proof system, verification is very easy. It's really syntactic. You check whether something is an axiom, you check whether it follows by a deduction. Here's a set of theorems, maybe more interesting than the previous two. We have famous theorems like that are infinitely many prime, Fermat's last theorem, and so on. But anyway, it's a proof system. So I've given you 3 or 4 examples of very different proof systems. Let's try to see what's common to all of them, what they share. This is a part of the methodology of our field. We want to classify a notion, let's say, all proof systems. So what are the essentials of a proof system? Well, completeness, meaning true claims do have proofs. And on the other hand, soundness, false claims don't have proofs. The 2 obvious things we expect. And the third one, which I stressed, is that verification is a simple procedure. An efficient algorithm. And again, I'm using for efficient algorithms something that runs in polynomial time, the length of the claim. Other notions were studied, but I'm not going to talk about them. And making this precise is this complexity theoretic view that was done by Cook and Recha. They just formalize these 2 notions. In what sense? A proof system is simply an algorithm. It's an algorithm we call a verifier. This algorithm takes 2 arguments. One is called 2 inputs. One is called the claim. The other is an argument. And it should satisfy what we saw before. Completeness, namely, if the claim is true, then some argument convinces the verifier to accept. This is the happy case where we call, the claim a theorem and the argument a proof. And then is that if the claim is false, then no matter what argument you supply this algorithm, it will reject. Okay. For each such proof system B, defined by the verifier, we have the set of theorems the verifier accepts T sub V. And it's very easy to see in any other definition of NP, the class NP, that NP is really the collection, the family of sets T sub V for all efficient algorithms V, all verified. It's also, so we saw examples, composite numbers, Sudoku puzzles are sets of theorems that are in NP. And it's also easy, again, if you have another definition of polynomial time, computable problems. These are exactly what verifiers can compute without looking at the argument. So they can take the claim and decide by themselves if it's true or false. So that's another way to explain the P versus NP problem, is showing that it's really, again, proofs versus computation. Okay, so far I was, doing the classical stuff. No errors, nothing. So I want to move there. And before I talk about errors in proofs, I want to just have one slide about errors in computation, namely probabilistic algorithms. I'm sure that you have all seen them. I do. Okay, so probabilistic algorithms, where do they come from? They come from our belief that nature supplies us with unpredictable phenomena, and so we can use it in algorithms. Right? That's basically the idea, use random choices in algorithms. And to define probabilistic one, let me contrast them with deterministic one. So deterministic algorithm A, let's say for some function f, is one which always, for every input, a of x equals f of x. That's a deterministic algorithm. For probabilistic algorithm, let's say B, because it uses random choices, the output is a random variable. So what we want, we insist that it's a good probabilistic algorithm for f if it values, if this random variable takes the correct value f of x, at least, let's say, 2/3 of the time, some number bigger than a half. Okay, so we call this with high probability. So this is a place where we introduce errors in algorithms. We allow errors, we accept errors. Error in the definition, an error is a third. This 1/3 error may not be sufficient for us. Maybe we want much smaller error. That's not a problem. And that's why this definition is as good as any other with other error, because error can be reduced efficiently. If we have an algorithm with error 1/3, let's say, we can run it many times, k times, independently, and then take a majority vote. And then the probability of error goes exponentially down with k. So errors can be made as small as we want. What's the value of allowing errors? Well, obviously, we seem to get a lot of mileage from probabilistic algorithms. We seem to be able to solve many more problems using randomness than without. And we don't know that. We believe that, but we don't know that. This is a good topic for another lecture, and I talked about it a bit. Why are we allowing errors? Well, I don't know, everybody decides for themselves, but we seem to tolerate errors everywhere else in life. If we cross the street, we are not 100% sure we'll get to the other side. Why not in algorithm? And so we have them and we use them all the time. This is, now that we know what probabilistic algorithms and errors there are, it's very easy to define probabilistic proof systems because proof systems were defined using algorithms, the verifier. So we just make the verifier probabilistic. Let the verifier be probabilistic, and of course we allow errors, so we allow that both the completeness and the soundness hold only with high probability, as high as we want, right? And here we introduce errors in proofs. Somehow this looks different than the previous slides, error in algorithms, mainly because, especially for mathematicians, proofs are holy, proofs are sacred, proofs have to be absolutely correct. That's how we know, what is true and what is not in mathematics. Why are we allowing errors in proofs? Well, let's flow with this and we'll see why. Anyway, in the same way we defined before, we can also now define what's a class of theorems provable by this type of proof system, what's accepted with high probability. And we call this class IP for interactive proof, which I should tell you that I didn't finish the definition yet. We are allowing verifiers to be probabilistic, but we will also allow them to be interactive, as I will explain now. So IP will be the set of theorems provable by probabilistic interactive proofs. So what is this interaction? I'll compare this idea, this definition of probabilistic interactive proof came to be in two independent papers in 1985, coming from very different definitions, Babai from group theory and Goldwasser, Mikhail Rakov from cryptography, but they define the same object. So the classical proof system, which we saw in the beginning, without randomness, is this argument sent by a prover to a deterministic verifier with no error. And IP, as we said, we allow the verifier to be probabilistic, to toss coins. Acceptance, is only with high probability. And one more thing we change is the interaction between them. So in NP, there's only one message from the prover to the verifier, the argument. Here we allow the verifier to interact with the prover, actually ask questions and basically ask whatever they like. And after this conversation with the prover, they decide whether to accept or reject. So it's a different model, it's a new model, which is a computational model of proofs. And whenever you have a new model, you should justify it, you should think whether it's reasonable or not. I would say that's certainly reasonable in the sense that we have at least two examples from life where interaction happens and errors happen. When we teach a class or when we interact with fellow mathematicians, there is an interaction going on. The fact that there may be errors is clear. So it seems reasonable. What I want to stress is that reasonable or not, you don't have to study only a reasonable model. You can study any model you like, at least in math. This is an absolutely revolutionary scientific notion. The birth of this model was absolutely revolutionary for lots of things. It had a big impact theoretically, practically, conceptually on society. I'm not going to go into these aspects. I want to discuss mainly, there are many variations of the definition I gave and so on. I will not go into this. What I want to talk about, is some paradoxical properties that proof systems, which are interactive and probabilistic and have errors, can have, which normal proof systems don't. I'll focus on two of them, and I'll just be brief, but tell you about zero-knowledge proofs and probabilistically checkable proofs. We'll see in more detail what they are. But also, as part of the story, how we, the evolution moved between them and to many more proof systems that I will define a little later. Let me talk first about zero-knowledge interactive proofs. They were introduced in the original paper of Goldwasser, Mikhail Rakov for cryptographic reasons. So a zero-knowledge interactive proof is simply an interactive proof. I should maybe stress that defining it formally is highly non-trivial, but the intuition is very simple. You want it to be an interactive proof plus a very strong demand. The demand is that the verifier, if it accepts, if it believes the claim is true, believes the prover, then at the end of the conversation, it knows nothing more than the fact that the claim is true. Nothing more than it knew before. It learned absolutely nothing. This looks very paradoxical. I mean, it seems that you think about the last time you convinced someone, a friend, about something they didn't believe and didn't give any new information. It sounds completely impossible. Actually, and you can think about example, how would a mathematician, convince another mathematician that the Riemann hypothesis is true without giving any information. Still, what we showed a year later is that, in fact, it's not only possible, it's universal. Everything which has a proof has a zero-knowledge proof. So the theorem more precisely, with Goldreich and Mikali, was that if you believe cryptography, if you believe that one-way functions exist, which it seems that the whole world believes, right? I mean, using security on the internet. If you believe that, then every problem in NP, everything classically provable, is also provable in an interactive proof zero knowledge. I'm not going to explain how to do it. I just want to say that this had, again, enormous impact in theory for cryptographic protocols. It is embedded in many practical systems. People extended this to a variety of physical analogs of zero-knowledge proof. The most interesting one, I think, is to nuclear disarmament, although I don't think it's used. But I want to focus again on more proof systems, and this led to the generation of more proof systems. I want to talk about them next. In particular, MIP, many prover interactive proofs that somehow magically follows from zero-knowledge proof. So I want to explain how. So here again is a picture of zero-knowledge interactive proofs. And I remind you of this theorem saying that if one-way functions exist, then we can do this magic, and everything provable is provable in zero-knowledge. Another aspect of the methodology of complexity theory is to always inspect the assumption. And we have here the assumption that while it's generally acceptable, you wonder whether it's necessary, whether it's really necessary to use cryptography in order to have zero-knowledge proofs, non-trivial zero-knowledge proofs. And the answer is, like often happens, yes and no. It's yes, because, well, we proved, Farostowski and me, that if you have a non-trivial zero-knowledge proof, then one-way functions exist. So it's essential for zero-knowledge proof. However, this theorem was proved for this model of which we just talked about, interactive proof with a single prover. You can do without cryptography, so the answer can be no if you move to yet another model of proof. And I want to describe it. This is a model where you have several provers. So specifically, we'll talk about two-prover systems here. We have, again, a claim, but there are three parties. There is a verifier who wants to know, and it can ask questions of two provers. And the important thing is that these two provers, while they can meet in advance and make a strategy and so on, after the verifier starts talking to them, they are separated. They cannot communicate. So the verifier then interrogates them both and decides whether to accept or reject. It's a new model. In this new model, we proved in this paper that you don't need cryptography. In this model, zero knowledge is possible for any claim without any assumptions. In some sense, the physical separation of the prover sort of replaces the use of cryptography. You can check them against each other. It's a new model, as I said before. We should inspect whether it's reasonable or not. I can tell you one funny story. At least it seems reasonable in the eyes of the two institutions we were at the time, MIT and the Hebrew University. They believed that it should be patented. So certainly they believe that it's practical and may make money. This was against our advice, and indeed nothing happened from this patent. But another place where it sounds reasonable is we know it's used in practice, like if a police catches, two suspects in the same crime, they will often put them in separate cells and interrogate them independently, trying to find inconsistencies and so on. So, reasonable or not, we are continuing to study this model. And so far we've seen that, we've defined this sequence of models, NP, the classical one, IP, one prover system, two prover systems, you can move 3, 4 and provers. And they seem to be bigger and bigger. And the question is, what is the computation power needed to compute any problem provable in one of them? Or in other words, what is the class of problem that can be proved in any one of these systems? And from the beginning, there were sort of trivial inclusions. It was very easy to see that anything provable by a single prover is in polynomial space. Don't worry if you don't know these classes. It's not really important. I just want to say that there were computational complexity classes, one involving space complexity and the second involving time complexity, which captures at least an upper bound on the computational power of this proof system. For two prover or many prover, turns out that non-deterministic exponential time was sufficient. But people believe that these inclusions were very, weak, and stronger ones will be found. And then, within a year or two, sort of magically, they were understood completely, and not only understood the power of this proof system. And in particular, what was understood is that these upper bounds I showed you on the previous slide are exact. IP exactly equals p-space. 2IP is exactly equal non-deterministic exponential time, and I'll talk about NP in a second. All these theorems hold without any assumption, no cryptography. And even if you don't understand the acronyms, I want to stress that each one of these theorems have a very strong intuitive content. It's really meaningful. For example, in the first one, it really says that winning strategies are provable to efficient verifiers. This is very surprising because they are not a statement about factoring of a number. There exist two smaller numbers that multiply to it. The statements of this type, there exists something so that something holds. In winning strategy, suppose I claim that I have a winning strategy in chess. It's not enough that I show you my first move. There exists a first move that wins, because then you say, but what do you do to this move of mine? And then I say, there exists another move that I can do now. And then for any move of yours, I can do this. So an alternating chain of quantifiers, statements of this type, can be proved in a proof system, in this interactive proof system. And similarly to the other one. I want to talk about the last one, which is sort of stunning again, very paradoxical, the probabilistically checkable proofs in this actually two papers. I want to explain it in a slide. So what are probabilistically checkable proofs? It's again another model. It's a non-interactive model like NP. So a prover sends an argument to a verifier. The verifier is probabilistic. It allows to make errors, very small probability. So PCP is the name, probabilistically checkable proofs. And again, there is another demand, very different demand than zero knowledge on the verifier. The verifier is restricted, even though it gets the whole argument, the whole paper. It can read only, let's say, 20 bits, maybe at random, from this argument, and on the basis of this tiny information, it will decide whether to accept or reject. Like before, this seems very, paradoxical or impossible. I mean, we know from our experience, we get a 100-page paper. How do we know if there's a bug there or not? We certainly cannot read a random line in a random page and know whether it's correct or not. And also here, it turns out that, this model, this kind of type of proof, is universal. Anything provable at all by the normal means of writing paper and the mathematical proof, any proof at all can be turned into another proof for the same claim, which has this very robust property. It can be verified with high probability just by sampling a few bits in the proof. That's the content of this PCP theorem, an absolutely fundamental theorem. Andrea mentioned NP completeness as a fundamental result of the field of complexity theory in the 70s. In the 90s, this revolution came, and the first thing it seems to offer is to relieve us of all our refereeing duties. I don't know that it was implemented yet, so I think we still have to read papers. But I want to say this conversion of a normal proof to a PCP format, to a robust format, is an efficient procedure that can, in principle, be applied. The impact of this was theoretical, and it was really revolutionary. It allowed the first time to argue about hardness of approximation for optimization problems. In a sense, NP completeness allows us to argue that finding optimal solutions are hard, and this theorem allows to argue that even approximating the optimum is difficult. Had vast implications in coding theory, circuit complexity theory in general, and it also is embedded in some living systems, including blockchain technology, cloud computing, and more. Absolutely fundamental result. Okay, good. We are done with the multiple provers, at least when we talk about probabilistic proof systems. We saw these two major theorems and the PCP theorem as characterizations of what can you do with one prover, with two provers, if you are an efficient probabilistic verifier. And now we are going to move to yet another world, from the probabilistic world to the quantum world. So we are going to allow everybody to be quantum mechanical. In order to talk about quantum proofs, I have to again go back and talk first about quantum algorithms. So I'll give you, like before, one slide background on quantum algorithms and quantum computation. Again, it comes from this belief that nature has for us quantum phenomena, so why not use it in algorithms? This was suggested by Feynman and Manin in the 80s. They basically suggest let's implement quantum mechanics into our algorithms so that they may manipulate quantum superpositions using unitary operations. If you've never seen this, again, it doesn't matter. It's a more magical power to the hardware we have. Like before, we allowed it to toss coins. It took time to formalize this model, to make a quantum Turing machine, like we had deterministic Turing machines, probabilistic Turing machines, also quantum Turing machines are more subtle to define. But we know we have a notion of PQP, namely the class of all problems solvable by efficient quantum algorithms. And having quantum power is stronger than having randomness. It's very easy to see that so you can do at least as much as you can do with probabilistic algorithms. Again, we allow error, tiny error. And then people played with trying to find algorithms for this hypothetical model. Again, a couple of years later, there was this bombshell of Peter Shaw. He proved that in this hypothetical model, in polynomial time on a quantum computer, you can factor integers and you can compute discrete logarithms. This, of course, is a bombshell because these are the very problems on which security on the internet rests. In the many systems that are out there where we shop online and do other things, we assume that factoring is hard. So now it seems that if anybody builds a quantum computer, we can forget about security and privacy and so on. So of course this caused major action, frenzy attempts to, first of all, develop the technology, building quantum computers. Billions were invested by companies and by governments and are still, being invested in order to build quantum computers. The jury is out. We don't know yet if they'll succeed or not. They certainly have developed amazing technology, and in particular also very important error correcting mechanisms for quantum errors. But if you think about quantum, about factoring integers, I think the largest integer that can be factored on these machines is maybe 65. So we have some ways to go. But yeah, it's amazing technological progress on this first item. Of course, also cryptographers started worrying, and today there's what's called post-quantum cryptography, in which you're trying to build systems which rest on assumptions, computational assumptions, that are not known to have quantum algorithms. And in fact, systems are replaced with assumptions usually resting on lattice theoretic problems, where we don't have quantum algorithms. People are continuing to try to develop algorithms, although we don't have many new ones. And what I want to again talk about is how they lead to new proof systems. So that's the last part of the talk, another 10 minutes. I want to talk about quantum proof systems. So we don't have quantum algorithms or don't have quantum machines, but we can hypothesize how quantum proof systems will look like. And again, because the verifier is an algorithm, we can easily define them because we just let the verifier be a quantum algorithm. The provers are infinitely powerful so they can do anything, including quantum algorithms. The first to define this formally was Watrous. He defined an analog. When I have a star, it means quantum. So an analog is a one-prover probabilistic quantum proof system. And the question, what's the power of this system? It took a decade. It's much harder than the classical setting, but still, series of works led to this result, showing that quantum one-prover systems are not more powerful than probabilistic one-prover systems. They capture the same class polynomial space. People also defined analogs of an analog of the many-prover, let's say two-prover interactive proofs. And here, a big surprise came because people believe that also in the many-prover case, it will eventually be found that it's not more powerful than the classical one. It took time even to prove that it's at least as strong as the classical one, as the probabilistic one, because you increase the power both of the prover and of the verifier and the prover. So people realize that it at least contains, the classical one, contains non-deterministic exponential time. And the surprise here came in the next paper, which shows it contains a much bigger class, doubly exponential non-deterministic time. So something was off. And the question is how powerful, what's the complexity of problems provable to an efficient verifier in this quantum model? And the result came a few years ago, and I mentioned this on my title slide. This class, this quantum proof system with two provers, say, contains not only arbitrarily complex problems, they contain even undecidable problems, the class RE, in particular, the halting problem. And this is a very difficult statement to digest, I think. I understand part of this book, and it's still very mysterious how you can convince a verifier running in polynomial time that, given Turing machine holds. It's a bit mind-boggling. Anyway, at this point, if you are a mathematician or even a computer scientist, you can say, okay, these complexity theorists are playing these games and they are looking at ridiculous, proof systems and they get weird results and, who cares? Well, it turns out that many people care, and this theorem had amazing consequences in mathematics. It resolved major open problems in several areas. Quantum information theories resolved the so-called Thilson problem. I will not define them. In von Neumann algebras, the very famous Korn's embedding problem or conjecture. In group theory, I should mention that very recently, like a couple of months ago, similar techniques using quantum proof systems, I'm mentioning it only because I know there are many probabilists in the audience and maybe listening. Italy is famous for its strength in probability. There's a very famous conjecture, the Aldous-Lyons conjecture. This was refuted using similar techniques. So the theorem or the proof embodies a technique that is extremely useful to mathematics and physics. So it's not just a game we play. So in the last couple of slides, I'll just explain one view of this MIP star, which is very interesting and how it relates to physics. I'll talk about this in the next slide, so let's see. So first I want to, again, tell you about two-prover systems in the classical and quantum case. It turns out that in this model, you might as well assume that the verifier asks only one question from each prover. It's like a one round is enough. We don't really need to say what the claim is because it's embedded in the verifier definition whether to accept or reject. So, the verifier talks to them, asks a question, gets an answer from each one. It has these 4 parameters and decides using them whether to accept or reject. And we can define the value of the game as the maximum probability that the verifier accepts this set of questions and answers. So of course, let's say what they are trying to convince the verifier in a false claim. What would be the maximum probability of that? We know that there is a gap between acceptance and rejection. One is with high probability, and the other with very low probability. So it's basically all about the value of this game. Given the verifier what the function is, we can at least define what's the value. This is in the classical case. Turns out that it doesn't matter at all. We said the verifiers, the prover cannot communicate, but if they share a random string, let's say there's a random sequence in the sky they can both look at, it doesn't change the value. The quantum version is the same thing, only that the provers here are allowed to share what's called an entanglement, a quantum state that they measure. It's like reading quantum information. It's basically by measurements. Again, you don't have to think about it, but this is a different game, and it also has a value star, okay, for a particular verifier decision of the 4 parameters. What is interesting is that this computer science view here, we care about this hardness of approximating, when the computational problem to know whether a verifier accepts or rejects, basically to have a good approximation of the value. And I already told you the theorems known about this classes. What is the complexity? But it turned out that physicists looked at exactly this model a century earlier. This happened at the Institute in the famous EPR experiment. Einstein and his postdocs Podolsky and Rosen suggested this, thought experiment that if you have a little imagination, you can see it as a two-polar system. So I'm sure many of you have seen this. You collide electrons, there's the photons that are being sent to two opposite directions in the speed of light, and then somehow if they are measured in one side, the other side is determined. This is the paradox that Einstein suggested. Here you want to, they call EPR, called this second case a quantum non-local game because there's no local, you cannot talk to each other because you are farther than the speed of light. And they call this weird possibility spooky action at a distance. They also looked for explanations that are classical. They basically look like standard two-polar systems, local games, and they wanted to explain what happens in the quantum world by maybe hidden variables, which can be thought of as a random string. So really the same question appeared a century earlier. And they were looking for examples of games, of verifiers, for which quantum can achieve a higher probability of success, of convincing, than classical ones. And indeed they did. They asked the question then, and Bell, famous Bell paper in '64, and then a sequence of other papers, showed that indeed there are, like quantum mechanics allows something that the classical worlds cannot explain. It suggested these tests, which were actually carried out in labs, sort of verifying practically that quantum mechanics work. So this was amazing. There are many examples like this known. The complexity theoretic side, as I mentioned, we like to classify things, and the sort of effort was trying to understand not just examples of games, but I'm trying to understand all these non-local games. And this approach is what drove this sequence of papers, in particular using previous results in the classical world about PCPs and proof systems, leading to this final breakthrough and all these implications. Let me summarize. We saw lots of proof systems. We saw that interaction, randomness, and errors lead to magical proof systems and also to lots of other important mathematical and scientific results. There are many connections that are revealed, and I think this is true about lots of complexity theory subdisciplines that connect to mathematics and physics and among each other. And I mentioned already this power of this methodology that comes in the development of these proof systems and their understanding. Okay, let me finish with my favorite slide. I wrote this book 5 years ago, and for those who want to know more on complexity theory, can get it free on my website. Thank you very much.